Okay, so what I wanted to do next is to give some example of the most striking sample spaces, which will be used actually very often, and they basically consist in spaces of coin tossings. So coin tossing are super. I mean, mathematicians are simple people, and they're interested mainly in coin tosses. But actually, um, I mean, let me first use the coin toss analogy, and then explain why it might be useful also. So let's share. Let me share my screen. Okay. Uh, so um, let me give some examples. So so the first example is the one of one coin toss. So here, what are the possible outcomes? The possible outcomes are heads or tails. So however you want to encode it, it will have the sample space will have two elements, which are 0 and 1, or the same, heads or tails, where of course the H or 0 means that the coin shows the face heads, and tails, one is tails, or maybe you can choose whatever you prefer. Um, then there is the sample space of two coin tosses. So let me use this notation. So omega 1 is the one stands for the number of tosses. So here we'll have to write omega 2. So how do we write this? Well, we have written the sample space of two dice rolled. We can use the same methodology, so we can we can use two digits. The first one denotes the result of the first coin toss, and the second one of the second. So in this case, 0, 0 means heads, that the first coin gave heads, and the second one gave heads, and 0, 1, the first one gave heads, and the second one tails, and so on and so on. So, for instance, if we want to write the event, the first coin gave heads, this would be the following event: 0, 0, and 0, 1, because we fixed the first digit to be 0. Then we skip omega 3, and we go to a general n, simply to get you used to mathematical notation. Omega n is the space of n coin tosses, where n is a natural number. So omega n, how can we write it? Well, it is the set, in this case, we can use the same encoding. We can encode the sample space with strings of n digits where the position of the digit denotes which coin the number refers to, and the number, which actually could be whatever symbol, but in this case, which well, the number denotes the result of the coin, 0 or 1. So let me try to write it this space. So there is the first one, which is all zeros until the nth digit. Then zeros and one, etc., etc. I could list it in this way, but I mean, it is for a general n, it is quite difficult. So let me write it in another way, which is following, like the set of strings of n digits. So I will denote each digit as xi, so x1, x2, etc., etc., up to xn. These are the digits. So where xi is in 0 and 1. So the digits are either 0 and 1, and there is a total of n digits. So I goes from 1 to n. So this is a way to write it. It's exactly what it is written above. So omega n is the set of strings with n digits, where each digit belongs to 0 or 1. Do you, uh, is it clear? Do you have any questions? No? Okay. So this is the state space of n coin tosses. It's not really different. It's only length more from the one of two coin tosses. It's only more longer. And now let's do another one, which is this the sample space of a finite amount of coin tosses, but a finite but undetermined uh, undetermined amount of coin tosses. What does it mean? Like you know for sure that you will stop tossing a coin, but you don't know when exactly. How can we write this sample space? Okay, so uh, mm, how can we write the sample space? Well, is the set the sample space can be encoded as the set of strings of finite strings uh, with digits in 0 or 1, where the position of the digit refers to which coin you tossed. Which coin, so the number, so sorry, where the number of where the numbers refers to the outcome of the coin toss whose number, sorry, it is more difficult. It is more difficult to say it than to write it. So we have a string. Each position refers to a coin toss, and the value of the digit it tells you if it is heads or tails. So this can be written in the following way. As the set of strings of n digits, finite strings, where n now varies in the real numbers. And xi is in 0 and 1. Can be either 0 or 1. So in particular, omega can be written in this way. Can be either, I don't know, if there is only one coin toss, can be 0 and 1. Then if there are two coin tosses, can be 0, 0, 0, 1, 1, 0, 1, 1. Then if there are three coin tosses, etc., etc. And we can see that this is also equal to the so I've written this set in three different ways. So the first one is like the set of strings with n digits where the digits belong to 0 and 1. The second one, I've listed them all along, and so this one is the union, like omega is the union of I mean, if the of the omega n's, where omega n is the one is this one. Okay, so it is. I don't know if it is clear this sample space. So in this space, there are no infinite sequences. Every sequence is finite. So you stop eventually tossing a coin. So you will have an exercise for next week, which has a similar sample space. So maybe if you have questions. I mean, it will be it is so I mean, well, if not, I go on. And the following example is an infinite amount of coin tosses. So this is quite a different example in nature. I mean, the other examples are all very similar. One which this one is much more difficult because, for instance, let me first write the sample space. Well, it's the space of infinite sequences, so x1, x2, etc., where xi is in 0 or 1 for each I. So is the set of the sample space is the set of infinite sequences with these values. Now, this is, I mean, do you have questions concerning these spaces? Why I'm saying that this one is very different from the other one? Well, because I cannot list it in this way, simply because of that. So in the example number 4, the one of a finite amount, I could have, it is an infinite sample space because there are an infinite amount of ways of tossing. So we can, but we can list it in this way. So we can write omega as a list of elements with some dots at the end. You know how it will go on. Now I can I'm sure that you will not be able to write the sample space in the example 5, the one of an infinite amount of coin tosses, in such a way, so listing all the outcomes. It is impossible because there are much more elements, and this actually is we will not consider this kind of sample space. So example number 5 has the peculiarity, not peculiarity, has the property that that omega cannot be written as a list of elements. That is in this way. Omega 1, omega 2, eccetera, eccetera. This is a theorem. It is known because in jargon this is written as omega is uncountable. We will not consider omegas that cannot be written as a list. Why is that? Because it is much more difficult and not much more difficult, but there are some subtleties which is not worth studying, and it would require like a course in analysis. So it's not it is not a big deal though, because I mean these omegas are already sufficiently interesting, so we don't need to deal with these ones. So simply, I wanted to tell you these four examples. Um, Now, if you want to do the exercise like the one of the first file of the first file, maybe I can share my screen. Maybe I can give you some minutes to do them. I don't know if otherwise I go on with the definition of probabilities, but maybe it's better to do these exercises in class. So let's okay. I mean these ones. So maybe I will leave you 20 minutes and then I will correct them. Is that okay? I'm here if you want any to ask anything, just simply write.